close this. Okay, good afternoon, everyone. So the topic of my presentation today is local clustering coefficient-based degree centrality. This is in the area of network science, where we analyze large complex networks using graph theory algorithms. So more specifically, we are going to focus today on what is called centrality metrics, which are used to quantify the topological importance of nodes in a network modeled as a graph. So there are a lot of centrality metrics out there. The more commonly used ones I have listed here, and they can be broadly grouped under two classes. Either they are neighborhood based or shortest path based. And neighborhood-based metrics are like degree centrality, eigenvector centrality, local clustering coefficient, and so on. So they're all computed using the neighborhood information of the nodes. And the shortest path-based metrics are like betweenness centrality and closeness centrality. So the computation of these metrics, as I mentioned here, can be what's called synchronous or asynchronous. So what it means is, so if I want to find the degree of a node, which is number of neighbors of a node, I just need to execute that algorithm just on that node and I'll get its neighbors or the count of its neighbors. Whereas for some other metrics like eigenvector centrality, even if I want to compute that for a particular node, I have to run that algorithm on all the nodes that involving all nodes, I would say, and then only be able to get the eigenvector centrality for a particular node. At the same time, once you get for one node, you can get for every other node as well. So we have to compute for all the nodes, not for just one node, even if you're not interested in the node values for all the nodes in the network. So that is the drawback of synchronous approaches. Then also some of these metrics require just a local knowledge, like the local clustering coefficient or degree centrality. Whereas most of the metrics require global knowledge. That means you need to know about the entire network graph to compute these metrics. So there are a lot of overhead involved in computing these metrics. So one metric that is very much important and it's widely used for different applications is betweenness centrality. So it's a measure of the fraction of the shortest path between any two vertices that go through a vertex. So it's very critical for communication networks. You want to find which router is going to be more overloaded and so on. But it's a very computationally heavy metric. Its computation is synchronous as well as requires global knowledge. So that's the metric we are going to target here. And we are going to see, can we come up with something that is equivalent or similar to this metric, but it's very computationally light. It doesn't require much overhead and capture the same thing as what betweenness does. So we'll use this example as a running example during this presentation. So this is a graph of 8 vertices, and I'm showing here the centrality metric values for these vertices in this graph. So degree and eigenvector or measure of neighborhood. Local clustering coefficient is like, it's a hybrid. It captures both local neighborhood as well as shortest path. We'll talk about that detail as we proceed. And closeness and betweenness is a measure of shortest path. Okay, so let me just motivate how betweenness is computed. We're not going to look at the actual algorithm in detail. You need to run this breadth first search algorithm at every node so that we can find the length of the shortest paths from that node to every other node in the graph. And then you need to compute these fractions like this. So let me go over one example here. So betweenness for node 1. So node 1 is here. And we are going to find what pairs of vertices need to go through node 1 for shortest path communication. So 0 is over here, and 0 to 5 need to go. There's only one shortest path between 0 and 5, and that's of length 2, and that path goes through node 1. So one of the shortest paths go through node 1, and that's the fraction. Then between 0 and 6, there are two shortest paths. One is 0, 2, 4, 6, and the other is 0, 1, 5, 6, each of length 3. And one of these two shortest paths go through node 1. So this shortest path 0, 1, 5, 6 goes through node 1, whereas the other one 0, 2, 4, 6 doesn't go through node 1. So one of the two shortest paths go through node 1. Then 0 and 7, so on, 2 and 5. So between 2 and 5, there's a shortest path of length 2, but there's also like 2, 1, 5 and 2, 4, 5. So there are three shortest paths of length 2, and only one of them go through node 1. So you need to compute all fractions like this that go through node 1. So I have listed only those fractions that are pairs that go through node 1. So all the other pairs don't need to go through node 1. So sum up all these fractions, that's the betweenness centrality of node 1. And so you see the time complexity involved here. So you need to do that for all the nodes in the network. And that's how you get the betweenness centrality of all the nodes out here. So one, as I said, the motivation is to see if we can use any of the existing metrics as alternative for betweenness. But so the other four metrics are listed here. So I found the correlation coefficient between betweenness and each of the other four metrics. And this is what we get as the R square value of this correlation plot. So none of them are very close to 1. The one that's close to or larger is this correlation between local clustering coefficient betweenness. And that's the kind of the motivation for us to consider local clustering coefficient to develop the other metric I mentioned about the computation light metric that could be an equivalent for betweenness. So going to do something like a synthesis of a new metric, which I call it as LCC prime DC, which is local clustering coefficient based degree centrality, and LCC prime because you're going to actually use 1 minus of LCC times the degree centrality. So the kind of, if you think about it, even in day-to-day scenarios, if the neighbors of a vertex are not going to use the vertex for shortest path communication, then nobody else in the network is going to use the vertex for shortest path communication. So what it means is, so if you think a vertex is needed for shortest path communication, first its neighbors should use that vertex for shortest path communication. So if the neighbors of the vertex themselves are not using or not going through the vertex for shortest path communication, nobody else is going to go through that vertex. So that's the kind of our premise here that we are going to see how the neighbors are going to use the vertex for shortest path communication. And for that, the local clustering coefficient is a very useful metric because it captures or mathematically it's a probability that any two neighbors of a vertex are directly connected to each other. So that basically means if you have a vertex and its neighbors, what fraction of the neighbors are directly connected to each other. So that's like the probability. So and you can see this LCC is betweenness plot. Actually, the correlation is going to be like inverse. So that means betweenness is not proportional to local clustering coefficient. It's more equivalent to 1 minus of this. So that means if the neighbors of a vertex are directly connected to each other, they're not going to go through that vertex for shortest path communication. So we'll make use of this like this. So if A implies B, then not B implies not A. So that means if the neighbors of a vertex are going to use the vertex for shortest path communication, that means they're not directly connected to each other. So they need to go through this vertex. So that means that particular vertex should have a high 1 minus of LCC. So, and if there are several such neighbors on the vertex, which means the vertex has a high degree, then the vertex is likely to have a larger betweenness, because basically it means we have several neighbors and a majority of those neighbors pairs are not connected. They need to go through this vertex for shortest path communication, and such a vertex will have a high betweenness. As I said, if several neighbors go through a vertex, then the rest of the nodes in the network also go through the vertex. So we formulate this LCC prime DC as 1 minus LCC times the degree centrality. And we'll now go through a procedure of how to find the LCC and compute this 1 minus LCC times degree centrality. And for that, we will make use of something called the ego net of a vertex, which is nothing but a subgraph. For any vertex, we can build a graph that involves just the neighbors of the vertex as well as the edges connecting the neighbors of the vertex. So, for example, given this graph here for node 2, its neighbors are 0, 1, 3, and 4. So the ego net will have only 0, 1, 3, 4 as the vertices, and the edges connecting those neighbors as the edges here. So there are only 3, 4, 0, 1 on the two edges in this ego net. For node 5, its neighbors are 1, 3, 4, 6, and 7. And these are the edges connecting its neighbors, and so on. So let's go through this example to calculate this LCC. So given this graph, the degree of the vertices. So for example, for node, let's pick up node 5. It has 5 neighbors. And so the maximum number of edges connecting those 5 neighbors can be 5 times 5 minus 1 over 2. So this is basically like if you have n vertices, the number of edges you need to connect the n vertices pairwise is n times n minus 1 over 2. But when we saw the ego net here for node 5, we don't see that many edges, 10 edges. We just have these edges. So this is the actual number of edges, and this is the maximum possible number of edges connecting any two of the neighbors of node 5. So the local clustering coefficient is actually the fraction of these two. So we have like 1, 2, 3, 4 edges actually, but you can have 10 edges maximum connecting any two neighbors. So 4 over 10 is 0.4 is the local clustering coefficient of node 5. And 1 minus of that is 0.6 times the degree centrality, which is 5. So 0.6 times 5 is 3, which is the LCC prime DC of node 5. So like that, you can compute the LCC prime DC of all the vertices here. And if you rank them in the decreasing order, so node 5 has the largest LCC prime DC, and then node 4, 2.5, and so node 2, 2.67, then node 4, 2.5, and so on. This is the ranking of the vertices based on LCC prime DC. And then this is the betweenest centrality of all the vertices out there, which I also listed here. And if you rank the vertices based on the betweenest, this is the ranking. So you see the ranking is more or less the same other than just this 4, 2, and 2, 4. So this is again a motivation for us. So if you have an application where you want to just rank the vertices based on betweenest, we don't need to really spend time to compute the actual betweenest values of the vertices and then rank them. We can just compute the LCC prime DC values of the vertices and then rank them. And such a ranking of the vertices is going to be more closer to the ranking of the vertices based on betweenest centrality. And we could actually compute the Spearman's rank-based correlation coefficient to get a quantitative estimate of how close are the two rankings. And so I'll just walk over this procedure quickly. So you could rank the vertices based on betweenest. So the ranking convention we are following is the lower the betweenest, the smaller the tentative rank number, and larger the betweenest, the larger the number. So like 0, 0, and 0, the three vertices with 0 as betweenest, we'll just give a tentative rank as 1, 2, and 3. And then 4, 5, 6, and so on in the increasing order of betweenest. So the tentative rank numbers are this unique for each vertex, even though they have the same betweenest, we just give them numbers in increasing order. But the final rank is kind of what decides the overall ranking or correlation. So final rank is same as tentative rank if there's no tie. If there's a tie, the final rank is the average of the tentative rank numbers. So what it means, like in this case, you have 3 vertices with betweenest of 0. And the tentative rank numbers we gave them are 1, 2, and 3. So average of 1, 2, and 3 is like 1 plus 2 plus 3 divided by 3, which is 2. The final rank is 2 for all these 3 vertices. Whereas for the other vertices, the betweenest numbers are unique. No two vertices are the same betweenest. So final rank is same as tentative rank. So we follow the same criteria to determine the final ranking of vertices based on LCC prime DC. So we have a final rank for each of these two metrics. We can take the difference between the two final rankings and then square those differences. And sum of those squares of the differences in this case is 2. And then plug it in this formula here for computing the Spearman's rank-based correlation coefficient. And so it's 1 minus 6 times this 2 divided by, there are 8 vertices, so 8 times 8 square minus 1, and we get like 0.98, which is very close to 1. So this is again an indication that the ranking based on LCC prime DC is going to be very close to that of the ranking of betweenest centrality. And there's another way, another correlation metric also we can use to assess how close are these two going to be. It's called the concordance based correlation. So the Spearman's rank based correlations for network-wide or global ranking, whereas this one is like pairwise ranking. So what it means is, if I pick, say, two vertices, so let's pick up something here, say the pair 1, 4. So if the LCC prime DC of node 1, which is 2 given here, and is less than the LCC prime DC of node 4, which is 2.5. So 2 less than 2.5. So LCC prime DC of 1 is less than the LCC prime DC of 4. What can we say about the betweenness of 1 and 4? Is the betweenness of 1 also going to be less than the betweenness of 4? And we see that here. So the betweenness of node 1 is 2.33 and betweenness of node 4 is 4.33. And that's true. So if the LCC prime DC of Vi is less than of Vj, the betweenness of Vi is also less than Vj. Such a pair of vertices are called as concordant pairs. Similarly, if the other way, so for example, the LCC prime DC of node 2 is 2.67 greater than that of Vj, which is 1. The betweenness of Vi is also greater than between of Vj. So such a pair is also called concordant. Or if they are equal, then the other side also has to be equal. So like here, LCC prime DC of Vi equal to Vj, same as betweenness of Vi equal to betweenness of Vj. So we count such concordant pairs among all possible pairs of these 8 vertices. That will be like 28 pairs of vertices for 8 vertices. And then count also the discordant pairs among this. So this is only pair here, 2, 4, that's discordant in this example, because you see the 2.67 is greater than 2.5, but 4 less than 4.33. So that's called a discordant pair. So LCC prime DC of Vi greater than Vj, but betweenness of Vi is less than that of Vj. So the correlation coefficient is simply the number of concordant pairs minus the number of discordant pairs divided by the total number of pairs. So in this case, it will be 27 minus 1 divided by 28, that's 0.93. So again, concordance based, we see a high correlation between these two metrics. The last one we can also evaluate is the Pearson's correlation coefficient. That's a kind of a measure of how linearly the two are correlated. And if they're strongly correlated, we can actually use LCC prime DC to predict the betweenness of the vertices. So this is the procedure to calculate the Pearson's correlation coefficient. We have the LCC prime DC and betweenness values of vertices. We take the average of LCC prime DC and take the raw differences between the individual vertices values and the average, and then square those differences and find the sum of those squares. We do the same thing for betweenness. And the formula is this: the product of this raw differences, which is this, and sum is 19.17, divided by square root of the sum of the squares of the differences for these two metrics, and it comes out to be 0.9675, again very close to 1. So if you kind of do a linear regression and get an equation, this is the equation that relates LCC prime DC and betweenness. And so if I plot LCC prime DC of the vertices and then the betweenness, that line goes through like this. So the R square value with, and if you take a square root of this R square, that's what you get as the Pearson's correlation coefficient 0.9675 is also quite high here. So we can go one more step. We can use actual LCC prime DC of the vertices and plug them in this equation and predict the betweenness of the vertices. These are the predicted betweenness centrality values, and these are the actual betweenness centrality values of the vertices in that example, and find the residual errors and square them up and use this formula to compute the standard error of residuals. And denominator is the degrees of freedom, which is the number of observations minus number of model parameters. Number of observations is 8 because you have 8 vertices, and number of model parameters is 1 because you use LCC prime DC as a parameter in this equation and predict the betweenness. So that's 1 parameter. So the sum of the squares of the residual error is 2.137 divided by 8 minus 1, and square root of that is 0.55. So that's also a very low number in terms of the error in terms of the prediction. So we continue this approach and run this computer LCC prime DC vertices for several real world networks. So I'm showing here about 18 real world networks. And so I have color coded here. So the green and the dark green actually indicate a very strong correlation coefficient, the Pearson's correlation coefficients, Spearman and Kendall, and Gordon's correlation between LCC prime DC and betweeners. So likewise, I also calculate the correlation coefficient between degree and betweeners, closeness and betweeners, eigenvectors and betweeners. And the color coding is like this. So strong correlation, you have a green color or dark green color, and moderate correlation, you have like a yellow color, and then low B correlation, you have the blue color, and if you go negative, it's like a pink color or red, dark pink. So you see more green colors for LCC prime DC with respect to all the three correlation coefficients as compared the other correlation measures, especially eigenvector is very weakly correlated between us. And then degree, even though it's strongly correlated in terms of Pearson's, the other correlation, like based on concordance correlations, only moderately correlated with between us. So with respect to all the three measures, like pairwise comparison or a prediction or network-wide ranking, or even the actual prediction, you see LCC prime DC could be a good alternate for betweenness, and that's the kind of contribution in our research here. So LCC prime DC can be used to predict the betweenness values of vertices, as well as compare pairwise and also rank network-wide vertices. Instead of computing betweenness, we can go through LCC prime DC. And the computation is asynchronous in the sense that if you need the LCC prime DC of just two vertices and compare, you just need to compute the local clustering coefficient of just those two vertices and get this metric. Whereas for betweenness, you have to run the algorithm on all the vertices and come up with fractions like this, add up all those fractions and so on. So you cannot just compute the betweenness of one single vertex. You have to compute the betweenness of all the vertices together. So that's the kind of the drawback of betweenness and the computational complexity involved there. Whereas LCC prime DC can be computed asynchronously just for the vertex that we're interested at. And since it can be just computed for a particular vertex, we can run in parallel this algorithm. So we can compute LCC prime DC of all the vertices simultaneously in parallel. And that's very much suitable for autonomous systems, like all the military applications and so on. And there's no coordination that much needed. So if a vertex just knows its neighbors, that's good enough to compute this matrix. So there's not much coordination needed as well. So that's about this metric. If there are any questions, feel free to ask me.